Alrighty, welcome to section 11.2. This one's going to be about rational functions and, more importantly, how to graph them and how to think of them in terms of shifts from this parent function. So just like in all the other types of functions that we learned, you learn the basic function and you learn how to shift it based on transformations like translations, reflections, and dilations. So first, vocabulary word, rational function. This is any function. That means you're going to have something like y equals f of x. That's written as a ratio of two polynomials. So in this case, actually, you're going to have a denominator, and then you're going to have something here. You could even call it like g of x over h of x, where g of x and h of x are two polynomials. Now, they could be super simple. So the parent function for rational functions, is extremely simple. The numerator is the simplest polynomial of all, 1, and the denominator is pretty darn simple as well, just x. So the most basic graph is actually just inverse variation, y equals 1 over x, with the constant just called 1. So you need to memorize this parent graph based on this function, y equals 1 over x, and then anything else that you see later on, you can think of as a shift or a change to this basic parent graph. So try plugging in different x values. So when x is 1, 1 divided by 1, so over 1 up 1. When x is 2, you get out 1/2, because 1 divided by 2 is 1/2. Then you go over 3 up 1/3, over 4 up 1/4, over 20 up 1/20th. So no matter how big x gets, you're still going to go up, but it's a smaller and smaller and smaller fraction. Likewise, if you go over a half, so like right here, if you go over 1/2, 1 divided by 1/2 is 2. So your output would be 2. And again, when we talked about inverse variation, when one variable gets smaller, like here the x value is getting smaller, the y value is getting bigger by the same ratio. So as we divide by smaller and smaller fractions, the output gets larger and larger. And there should probably be an arrow at the end of these because they continue on forever upward and forever outward. The same exact thing is true on the negative side. Just if you divide by a negative number, you get out a negative number. So the coordinate points are all the same here as they are here, just in the negative quadrant instead of the positive quadrant. Okay, a couple more vocab words. Excluded values. As we said before, you can't divide by 0. So anytime that you would have something that gives you a 0 in the denominator, it's called an excluded value. Later on, we'll learn about something called extraneous solutions. Basically the same thing. Anytime you get a 0 in the denominator, whatever that point is not part of the 0. And so excluded values actually, these cause vertical asymptotes. We'll talk about what that is next. Vertical asymptote. Okay, so what is an asymptote? An asymptote is just a line that a graph approaches but does not cross. So let me redraw from the front slide that graph we had. So we have the curve that generally looks like this in the positive quadrant and like this in the negative quadrant. And now let me change my color. So we have this horizontal line right here. I'll draw it in dotted. This is actually the x-axis, but this line on this side, it gets closer and closer and closer but doesn't cross. And same thing over here, it gets closer and closer and closer but doesn't cross. So this one here is a horizontal asymptote. And for your most basic function, the horizontal asymptote is right there at the axis at y equals 0. Okay, then likewise we have a vertical asymptote. So this line is going up and up and up, but not crossing this vertical line here. And this one is going down, 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 but not crossing. So this we have is a vertical asymptote. And these kind of rational functions are pretty much always going to have a vertical asymptote and a horizontal asymptote. So you can get used to that. Now you can imagine if I shift this graph left or right, then my vertical asymptote is also going to be shifted left or right a certain amount. And my horizontal asymptote, if I shift this graph up or down, my horizontal asymptote will get shifted up and down. So the asymptote is the line that you approach but do not cross. The vertical, went back a slide, the vertical asymptote is caused by the denominator being 0, and the horizontal asymptote is caused by a shift up or down from 0. Okay, a couple problem-solving tips. Most rational functions can be thought of as your basic y equals 1 over x, and then shifting. So the way that you want to graph these is by imagining that basic function centered at 0, 0, and then if you've shifted left or right or up or down, you find that new center, and then you draw in new asymptotes. Okay, so we'll do some examples. Once you shift to the new center, you can draw in with dotted lines new asymptotes. So most rational functions, they're going to have those two asymptotes we talked about, one vertical, one horizontal. You can locate them by seeing where the new center is shifted left, right, up, or down. Vertical asymptotes, just to reiterate, occur where the denominator is 0, so you can't divide by 0. That gives you a vertical asymptote. And horizontal asymptotes, they normally start at y equals 0, which is the axis. But if you shift up or down by a certain amount, then the axis will also, or the horizontal asymptote will shift up or down with that axis. Okay, you need to memorize the parent graph for these functions, because that's how you're going to graph everything else. Over 1, up 1. Over 2, up a half. Over 3, up a third. Again, if you ever forget, you can just write down y equals 1 over x, and notice that as the denominator gets bigger, the fraction gets smaller. And then don't forget to plot the left side of the graph. There's a whole negative half to the graph as well. A lot of times people will plot the top right and totally forget about that bottom left. Alright, here's some examples. State the excluded values for each function. This is super easy. The excluded values are the ones that make the denominator 0. So here, x cannot equal 0. Super easy. This one, x cannot equal 2, because if I plug a 2 in here, I'll get out nothing. Right here, x cannot equal negative 6. So you're going to get whatever the opposite of this thing is, kind of like using the zero product property, only you're using it for the denominator instead of the numerator. Let's try this one here. X cannot equal positive 7. Okay, so you set this equal to 0, and then you solve. So finding excluded values is super easy. Set the denominator equal to 0, and then see what values of x. And then to say excluded, you just do an equal sign with a line through it. Alright, a couple of examples. Identify the asymptotes of each function, and then graph it. So this first one here, it's got x equals 0 and y equals 0 are the two asymptotes. So I got my horizontal asymptote right here, and I've got my vertical asymptote right here. I'm not stretched or shrunk at all, so I go over 1, up 1, over 2, up a half, over a half, up 2. Okay, and 3 points should be sufficient to plot this guy. I plot the positive side right here, and don't forget about that negative side. Back 1, down 1, back 2, down a half, back a half, down 2, and then I plot my curve. So again, you don't need a t-table to do these, although if you want to write it off to the side you can, but it's really just the same thing as you've always been doing. Okay, let's take a look at number 13. So my horizontal asymptote is still going to be y equals 0, because I have not shifted up or down at all, but my vertical asymptote, I've shifted to the right by 2 units. Notice this x minus 2 means 2 units to the right. So x equals 2 is going to be my new asymptote. So the first thing I do is I locate my new center, which is right here. And I draw in my asymptotes. I've got a vertical asymptote right here, and I've got a horizontal asymptote in the normal spot. Now let me change colors. When I draw in my graph, I just treat this as my new center. So I go over 1, up 1, over 2, up a half, over a half, up 2, and then I draw in my same old shape. Oh no, not the same shape. I've made a mistake, haven't I? So the reason that I've made a mistake is there's a 3 in the numerator. Okay, so let me cancel out the red and let me switch colors one more time. Let me switch and go purple on it. So normally I would go over 1, up 1, but because this 3 in the numerator means I'm stretching vertically by a factor of 3, I'm going to go over 1, up 3. Okay? Then I'm going to go over 3. Normally I'd go up a third, but instead I'm going to go over 3, up 1. Then I'm going to go over 2, up 1.5, over 1.5, up 2. So now I can draw in my graph. Notice that it's 3 times taller than it was going to be in every location. On the negative side, I go down 1, or sorry, backwards 1, down 3, backwards 3, down 1, backwards 1.5, down 2, backwards 2, down 1.5. Okay, then I draw in this curve, approaching but not crossing my asymptotes. And now the purple is the correct, and we want to just ignore that little red part because again, to reiterate, it was stretched vertically by a factor of 3. Okay, this last one here, this right here means it's gone left 1, so I go left 1. This right here means it's gone down 1, so I go left 1 and down 1. This is my new center, so I can draw in my asymptotes. And I'll switch colors again to do the actual graph. Now I have a stretch factor of 2. Okay, so from my center I go over 1 up 2, because I'm twice as tall, over 2 up 1, over 4 up a half, over a half up 4. So if you can plot like 3 or 4 points, that will give you a good basic value for where to put this guy. They all have the same shape, it just depends how tall they are. So backwards 2, down 1, backwards 1, down 2, backwards 4, down a half, backwards a half, down 4. Notice that I'm just choosing the values that work out nicely. So like 4 over 4 down a half, because it's stretched by a factor of 2. So this is nice whole numbers, that makes it easy. If that was too quick for you, by all means ask me to go over more of these in class or rewatch the video. I promise that with all the reflecting and translating and dilating you've been doing with parabolas and square root functions, this is just an extension of that same basic idea. Alrighty, I'll see you in class.